Yes, thank you very much. So first of all, I really would like to thank Professor Henneaux for the privilege he's giving to me to give this talk here at Collège de France. So yes, it hasn't been announced that this talk will be about Carrollian geometry that you have seen in the lecture, and more specifically, the conformal extension of this kind of geometry. I will explain why I need a conformal extension of what you saw during the lecture for my purposes. So just before the beginning, I have to tell you that I will present, roughly speaking, what was published in this paper, so Carrollian holographic derivation of Gravitational Flux-Balance Laws in Physical Review Letters. And it was written in collaboration with Simon Pécard from the CISA in Trieste, Marios Petropoulos from École Polytechnique, and Mathieu Villat from the Université de Mons in Belgium. So this is the outline of my talk. So first of all, for I think this audience, it will be great to review a bit what I mean by this was not the right button. So what I mean by the flat space holographic correspondence and why it is interesting from the first place. Then I will explain that this holographic perspective, there is interesting physics happening at the boundary, which is all the salt of this actually. And I will describe in the context of asymptotic flat space-times the kinematics and the dynamics that occur in this boundary, which will be endowed with Carrollian geometry and Carrollian physics. Therefore, it has this place in this series of lectures by Professor Henneaux. And then afterwards, I will describe what we actually did in the paper to advance our knowledge about this flat space holographic correspondence. And I will summarize and give some perspective for future work if some of you are interested to join the endeavor. Okay? So just before I start the serious things, please feel free to interrupt me at any time. I don't think I will cover my 1 hour and a half, so if you have technical or conceptual questions or remarks, please do not hesitate to interrupt me. Okay? So now that this is a broad introduction, just to be sure that the audience and myself are on the same page. So nowadays, in high-energy theoretical physics, let's say we are interested in finding a quantized version of gravity, so which is, roughly speaking, the union between gravity and quantum mechanics. Actually, this union has been more or less been done for 3 of the 4 the fundamental forces, which are described by quantum field theory on flat backgrounds. But regarding to gravity, is mainly modeled as a classical theory, which is Einstein's general relativity. The problem, let's say, with general relativity is that it breaks down at smaller scales. For instance, inside black holes, it predicts singularities. There are also tensions with observations in cosmology. The presence of dark matter or dark energy and the value of the cosmological constant are not very well explained within Einstein theory. And also, the quantum cosmologists expect some really strong effects in early universe. So just to give you some kind of motivations why actually we are interested in finding a theory of quantum gravity nowadays. So just to tell you where to look at, I will give you some widely accepted facts among our community. The first one is that black holes behave like thermal objects, with a temperature, roughly speaking, roughly given by the surface gravity of the black hole, and an entropy, which is proportional to the area of the horizons. You see, these are famous results for the 70s, so actually it's an old topic. And the second observation is that gravity should be built as a gauge theory for diffeomorphism. And for this, this analysis of gauge theory and their quantization, I refer to the lecture of Professor Henneaux in 23 and 24, actually. But maybe if you were following these lectures, or if you know something about gauge theories, you know that there is not only the first Noether theorem, but actually a second Noether theorem that tells you that the Noether current is actually a total derivative on shell. So, which means that your charges are not volume charge, like in usual, but are rather surface charges. It's also relates with the fact that in gravity you cannot localize the notion of energy or angular momentum because of the first equivalence principle. And then this energy and angular momenta have to be surface terms. So with this idea in mind, some people came at the end of the last century with this very nice idea of holography. And I would like to give you my definition of holography, which is the most used in the community at least, and which is the one given, roughly speaking, by 't Hooft and Susskind in the early 90s. So in a given space-time region, the gravitational degrees of freedom that are enclosed in this space-time region can be encoded on the boundary of one lower dimension. That basically is the boundary of this region. Okay, so for a large part of the community of theoretical physicists, this is one of the most promising routes towards quantizing gravity. And we have had a lot of hints explaining us that this is actually the case, even from the classical theory of gravity. For instance, this Marc Henneaux analysis that I will review in a minute. And we even have an explicit realization of this holographic principle in the case of a constant negative curvature spacetime, which are referred to as anti-de Sitter spacetime, ADS, which are actually thought to be dual to a conformal field theory, which is referred to as the ADS-EFT correspondence. So just to give you some hints in this ADS case, basically, so what is ADS? Is a solution of Einstein's equation with a negative cosmological constant, so which can be tracked as a constant negative curvature at infinity. So, okay, the cosmological constant is not negative in our spacetime, so it is a non-physical model, but it helps us a lot in understanding why holography is supposed to work from the first place. Indeed, in this kind of space-time, which you can represent to fixed ideas like a soda can like this, you can think of gravity in ADS as confined in a box like this, okay? And then it's easier, for instance, to define in such space-times a notion of boundary. So basically, the boundary is just the boundary of this can, if you wish. And what you can show is that on account of Einstein's equation, it is endowed with lower dimensional theory. For instance, if you are in 4 dimensions in the bulk, it will be a 3-dimensional theory on the boundary. And this 3-dimensional theory on the boundary will obey the rules of special relativistic physics. So it will be Lorentzian in the terminology of this lecture. Of course, and I will review why, actually, the Lorentzian structure at the boundary of this type of spacetime is not unique, but actually belongs to a conformal class of metric. And I will come back on that. But the thing is that since you have this conformal freedom, so the freedom to rescale lengths at will, actually, the symmetries are no longer isometries of a given metric, but are isometries of a conformal class of metrics, so which are the famous conformal isometries. Actually, they are finite dimensional if spacetime has a dimension greater or equal than 4, as shown again by Professor Henneaux and Claudio Teitelbaum in the 80s. And you have a surprise because if you go to 3 dimensions, then you have an infinite dimensional group at the boundary which consists of 2 copies of the Virasoro algebra. And this, asymptotic symmetry analysis is now famous under the Brown-Henneaux name from 86. And it was basically one of the first, if not the first, hint that holography should take place somewhere in this ADS setup, even before the idea of holography was raised. Why? Because actually these symmetries basically constrain a lot the boundary theory, which is a 2-dimensional conformal field theory. Okay, so then let me just give you some words about the solution space in this case. So the easiest way to get the Einstein solution space in the case of ADS is to take a patch of coordinates that I write omega and x mu, where x mu cover actually the coordinate on this conformal boundary here, so the boundary of the Ken that I depicted here. Then this boundary, I will call it scry, and it will be located at the vanishing point of this omega function, and I will refer to the interior of spacetime as the bulk. Then Einstein's equation in the bulk actually will imply that, as I already said, scry is a Lorentzian manifold with an effective speed of light which is proportional to the cosmological constant. Indeed, whenever you are Lorentzian, you impose at some point that you have a constant, which is the speed of light, that is invariant under any change of an inertial observer. And this is exactly what happens at the boundary of ADS, except that this is not the speed of light from the bulk, but this is an effective speed of light in 3 dimensions that is controlled by the value of the cosmological constant. Then you can basically solve Einstein's equation. It has been done in 85 by Pfefferman and Graham. And then you will see that actually this equation leaves 2 free data. These data are nothing but the boundary metric and something that you can find on the 3rd subleading order in the metric, which I will call T mu nu. And then if I impose the full Einstein's equation, then they will tell me that this T mu nu is actually conserved on the boundary and is even traceless in 4 dimensions. Okay, so this is basically the basics of gravity in ADS. So now, why this statement is again among the foundation of this ADS-CFT correspondence? It is because you can, according to this seminal paper, define a finite on-shell action that you can vary to get finite variational principle and finite charges. So I will not give detail about that because it will take too much time, but just trust me on this point. This renormalized action for gravity can exist, is finite on shell, and its variation is also finite. And what you do in a holographic context is supposing that the variation of this action corresponds to the variation of a boundary action that for the moment you are agnostic of, but you just suppose that it exists and is local. If this is the case, what you can show is that if you couple this boundary action with the boundary value of the gravitational field, which is this boundary metric, if you wish, to be precise, the gravitational potential to the gravitational field at the boundary, then you get this kind of equation upon variation. So this gives you a definition of what is called the covariant energy momentum tensor to a theory. It is in line with what Professor Henneaux just explained in his lecture just before. So that to derive energy and momentum from for a theory of fields, you have many ways to do that, but one very convenient one is to couple this theory with gravity, and then you derive with respect to the source of gravity, and you get the energy momentum tensor. So this T mu nu that you can find actually in the bulk metric field will be interpreted in this setting as a boundary energy momentum tensor that is referred to as the holographic energy momentum tensor. Actually, what you can show is that if you want to compute bulk graviton amplitudes, you just need to compute correlators on the boundary of this holographic energy momentum tensor, and then you will basically get a quantized linearized gravity in the bulk. This is one of the predictions of this holographic correspondence. Now, something that will be really important for us today is that since you have this expression, you can now ask if my boundary action obeys some variational symmetries, what are the consequences on this field T mu nu? First of all, since you are in gravity, you know that diffeomorphisms are present, and they are also present on the boundary. So what you can do is basically to check if this action is diffeomorphic invariance. Actually, you replace this delta by the Lie derivative on the metric, you perform some integration by part, and then what you get is basically this condition. So your boundary reaction is really diffeomorphic invariance because this was already implied by Bulk-Einstein's equation. You have also a Weyl invariance, meaning that you can change freely the conformal factor in front of the metric, which is referred to as a Weyl transformation. And so if you replace this delta G mu nu by a factor times G mu nu, what you get is this tracelessness of the holographic stress tensor, but which was already implied by Einstein's equation. So long story short, what you can do is just assume that you have a boundary theory that is local in some field. You couple it with the background geometry, you get this expression, and then by only imposing symmetries, you recover Einstein's equation in the bulk, which is kind of powerful. And let me stress that all of this is still classical. So just playing with symmetries. Okay? So I think Professor Henneaux will review this method to derive the stress tensor next week. So sorry by advance to spoiling the last lecture of, of this series. Okay, no question? So if not, let me continue. So the thing is that, as I've already told you, this ADS model is not really physical, right? Because it involves this negative cosmological constant, which is not observed in nature. Actually, in nature, what you can show is that our universe has a small, really small but positive cosmological constant. But actually, if you are not interested into phenomena happening at cosmological scales, you can basically neglect this cosmological constant. And then you are back to a model which is, let's say, flat or asymptotically flat if you have sources of gravitation that can curve the space, but in a local manner. You know? So you can curve in the bulk, but asymptotically, when you have a rarefaction of these sources of energy and momentum, basically that can curve space-time, you are back to flat space. Then, which is nice, because in flat space, we have all our beloved notion of spatial relativistic things, inertial observer, notion of clocks, etc., that we are going to use in holographic context. So actually, let me tell you that this model of asymptotically flat space-time is not something academic. It covers a very large class of situations, from collider physics, so to describe what is basically in the LHC, what is happening in the LHC, for instance. It describes the motion of planets, etc., around stars, so mainly what is called astrophysics, and also what I like to refer to as gravitational wave astronomy, which is really trendy nowadays, because of all these observations of gravitational waves and measurements in gravitational interferometer. So I like to say that actually flat space holography is bringing the world of holography into more concrete physics. But, this is the point, you have a price to pay for doing that. Because now we will be facing some challenge. Now your space-time do not like anymore like a can, but it looks like this kind of diamond. So it's just a representation of what the space-time is and where is the boundary. And here I represented the boundary as 45 lines. It's because now the boundary is populated by null arrays. So it's no longer Lorentzian. Actually, it is Carolian, because otherwise I will not be giving this talk here. So this is actually Carolian geometry that will happen at the boundary. And now, the conformal symmetries, which were finite dimensional, for instance, in 4D before, will become infinite dimensional, precisely because of the presence of an enhancement here of the translation in the Poincaré group. And this enhancement is referred to as the BMS group, coming from the Séminaire reference written by Bondy, Van der Burg, Metzner, and Sachs. And do not forget also the contribution by Sir Penrose. And again, if you need some recollections about this BMS story, I would like to refer you to the lecture of Professor Henneaux 4 or 3 years ago. Something really important as well compared to anti-de Sitter is that in anti-de Sitter, I have told you that we have the conservation of an energy momentum tensor. In flat space-time, actually, and it's known since 1962, since the work of this gentleman, actually, whenever you have bulk gravitational radiation happening, you don't have conservation of the charges at the boundary. So it's again a challenge, because now the dynamical equation will not look like the conservation of an object. but will look like more flux balance law, meaning that you will have the temporal variation of a charge giving rise to a flux. Hence the title of my talk, actually. So maybe I can just display this equation for you. So if I denote m, so the mass aspect of my spacetime, and na, the angular momentum aspect of my spacetime, and by which I mean, I am an observer here traveling close to null infinity. So basically, we are at this kind of, null infinity. Yes, so sorry, I have to tell you that since it's populated by null rays, it's referred to as null infinity. Okay? So then basically, what are the asymptotic observer traveling near null infinity? Sorry, they are us basically watching at stars. We are this kind of observer. So it's really physical. And then at each time here, so at each cut, a red cut in my drawing here, you can evaluate the mass and the angular momentum of your spacetime depending on to which direction you are heading to, basically. And this gives you a notion of mass and angular momentum. This mass and angular momentum play exactly the same role as the T mu nu in anti-de Sitter. They are found at third subleading order in the line element in this kind of space-time, and provide for you nice observables when you integrate we integrate them on the sphere. We get the total mass and the total angular momentum at a given time, basically. So if you define these quantities, what you can show is that they evolve on time. So for the moment, it's just notation, but I will explain everything in the following, but just to give you the flavor of what's going on in this talk. So you will have this kind of equations that are, for the red terms, these are just nabla mu of T mu nu split between time and space. Why do I have to split? Because you know that in Carolian geometry, I have a preferred direction of time, which is given by the field of observer, or the Carolian vector, and then it's customary to split everything between time and space. Okay, so this three term will basically be the nabla mu T mu nu of ADS, but there are more. There are all these blue terms that depends on the shear of null rays that are arriving at future null infinity. And I will represent this shear by this CAB and its time derivative by this NAB, which is nothing but the Bondi-News tensor. So already you see that there is some kind of discrepancy between the two case studies in holography. You have ADS with conservation equation, and you have flat space with something which looks a bit more awkward. So a fundamental question that you have to ask before proceeding with flat space holography is, do this equation have the same status as the conservation of the holographic stress tensor in ADS CFT? And the answer actually is yes. And I will show you in what sense. So yes, so this is the result that we were advocating for in this paper. So the boundary intrinsic derivation of BMS flux balance law in the same way as I reviewed for you in ADS can be done actually, and it works. But so when I say it works, so it means that it will follow again from diffeomorphism and Weyl invariance. That's it. These additional terms actually will come from the presence of this gravitational radiation that can now arrive at null infinity, and which we will interpret it as additional sources in the variational problem. Now, just to end with the motivation, so why it's important? Important for various reasons, but I've just here selected a couple of them. So it's nice to study this flat holographic correspondence, first of all, to test the limits of the holographic paradigm. Because, in ADS, everything is nice because you have this confining potential at large distances that, morally speaking, brings boundary information into the bulk. And then you can have this nice correspondence happening. But in flat space, you have null boundaries, you have non-conservation, you have a ton of things that usual people studying quantum mechanics and quantum field theory are not used to, actually. So if we can make the thing work in flat space-time, it's a good signal that actually, yes, gravity is holographic and that this holographic point of view can be applied to many different systems. So understanding also the derivation of this dynamical Einstein's equation is a fundamental building block for the reconstruction of any solution of Einstein's equation from boundary data. And also, something that will maybe it will be more interesting for some of you is that since the natural boundary of a black hole is also a null hypersurface, is the event horizon, all the techniques I will present to you today are also applicable to this surface. So whenever you have an apparent horizon, a cosmological horizon, an event horizon, etc., and you want to do an holographic reduction of the gravitational degrees of freedom on this hypersurface, the technique I will be presenting will help you. Okay? And the last point, I will come back on it in the conclusion. So this ends my long introduction, but I think it was good to bring everybody on the same page. So are there any questions so far? No? Okay, so maybe now I will enter into a part that will maybe be boring for you because you had the lecture of Professor Henneaux, but I need to be at some point self-contained. So I will first give you some reminder about conformal compactification, and then afterwards apply this to flat space-time and see that actually I have a Carolian manifold on my boundary of interest. So first of all, why do I need a conformal compactification? It's just that usually I'm studying a space-time like this with a boundary far, far away, so that I depicted by this fuzzy boundary here. So it is repelled at infinity, and technically I don't have even mathematically access to infinity. So the thing that I do, basically, and I follow a very nice idea from, again, Sir Penrose, is to start from this geometry, so this manifold n tilde endowed with a metric g tilde, and then I perform a diffeomorphism to remove basically the second order pole at infinity that any metric has in this. And then I will so define the diffeomorphism as follows, with an omega square here that will be tracking the pole. And I will say, okay, I have this function induced by my diffeomorphism. It's positive everywhere on the new manifold M without tilde, and it's vanishing at a boundary. So I will basically map a manifold without boundary, but with something happening at infinity, onto a manifold with boundary, and I will identify the boundary of this new manifold, which I depicted in red here, with the behavior at infinity of this original manifold. Okay, so this is just a mathematical construction, but it has a very nice physical interpretation in this sense. The price to pay, again, is that since the only qualification for this omega is that it's smooth and it vanishes at the boundary, does not fix it once for all. So I have basically to deal with an infinite dimensional class of these omegas. Basically, if I do this kind of change where b is a non-vanishing function, the construction since still go on, sorry. So then what I will have to deal with is, instead of just one metric, will be a conformal class of metric. So by which I mean really that I will have from one physical metric, I will start from one physical metric, and through this construction, I will have to deal with an infinite dimensional class of metric. At the level of the gravitational field, it's even more dramatic what's happening, because on the original space-time, so you know from your general relativity classes that actually the gravitational field on this geometry induced by the metric G tilde is what is called the Levi-Civita connection for G tilde, which is just a certain combination of the metric for it to be a connection. Okay? Derivative of the metric, sorry, for it to be a connection. In my new space-time here, which is unphysical but which is more tractable mathematically, the thing is that now if I prescribe one Levi-Civita connection for one metric, since the Levi-Civita connection is in one-to-one correspondence with the metric, the thing is that I will basically break this Weyl invariance. So I will break a symmetry which is not physical. it's never a good idea. So the thing is that I have better to work with what is called a Weil-Levi-Civita connection, which means this is the metric which is compatible with not only a metric, but the whole conformal class of metric. And I will be tempted to write an equation like that, where actually this A, referred to as a Weil connection, transforms inhomogeneously under this kind of transformations, in order for this equation to be preserved when I change my representative G by B minus 2 times G. So it's just a simple matter of computation to show that this is actually invariant. Actually, I have to add an additional background structure to my story. Indeed, because here I just had a metric, and here I have this omega. I have this, this conformally scaled class of metric, and I have on top of that to add this A. But this A has a really beautiful geometrical meaning, because, if I consider the normal one form to the boundary, basically it will be d omega, because the boundary is an omega equals constant hypersurface, minus something. And if I want this to be also a covariant under this transformation, so by which I will refer to as a Weil covariant, then I have to complete it in the bulk by something which will vanish on the boundary but transforms inhomogeneously, and this is the A I will be using to define my connection. So this is maybe the more technical part, the most technical slide of my talk, but I think it's important to be aware that whenever you want to talk about asymptotia, you cannot do it basically by taking, let's say, a radius to infinity. If you want to do things really seriously, you have to conformally compactify, and then you have to go through all this. Actually, it's not a drawback, it's more a feature of what you want to do. Because actually, this Weil symmetry is really constraining, and whenever you work within this formalism, you will be interested in finding Weil covariant object. And if you do that, basically, you find on the nose all the nicely transforming objects that you want to use to describe your gravitational theory. Okay? So now let's assume that Einstein's equations are solved by this unphysical metric. So let me recall you, this unphysical metric on the original manifold. And let's see what this equation implies on the unphysical one. So first of all, Scry is codimension 1, so this is fine because I needed a codimensional boundary, and it's null. So what you can show is that since it's null, if you take the normal, which I referred to nu in the previous slide, I raise an index and I call it epsilon. So this letter is epsilon. I call it like this, and what I can show on account of Einstein's equation is that this epsilon is null on the boundary. So then now, if you pull back this equation on the boundary and you take into account that epsilon is the normal vector to your boundary, you get this equation. And this is exactly what Professor Henneaux displayed to you as one of the structural definitions of a Carrollian manifold. But this is not enough, because you have also this Weil transformation inherited from the bulk, so meaning that you don't have just one normal and one metric. You have a conformal class of metric and a conformal class of normal. So these three equations are referred to as defining conformal Carrollian geometry. So this is the geometry I will play with. You notice that compare with ADS, the only difference is that I've become Carrollian. Why? Because recall that the speed of light at the boundary of ADS, the effective one, was proportional to the cosmological constant. Now this cosmological constant has gone to 0, so the effective speed of light has gone to 0 as well. Okay, so, and you see that sending the speed of light to 0 is basically congruous to Indo-Carrollian physics on the background manifold, as it was defined by Jean-Marc Lévy-Leblond in 1965. So this is something that basically, so the first point was expected in some sense, because this talk is about Carrollian physics. But the second one is even more interesting, because what you can show is that, so it's a bit of differential geometry. I'm sorry if I'm losing some people, but I need to go through it. So this manifold at the boundary is embedded into the space-time without intrinsic curvature, if you wish. The thing is that it's a bit difficult to define the notion of extrinsic curvature for null hypersurface, and we better talk about what is called the Weingarten map. But I don't want to enter into all these details. But if you want a precise statement for mathematicians in the audience, this statement can be seen as the fact that the Weingarten map of null infinity embedded into the unphysical manifold is proportional to identity. So this is just for technical terms, but what does it mean more physically, if I can say? It means that the shear of this Carolian vector epsilon vanishes, actually. And since this shear vanishes, we can determine the boundary connection from the bulk connection. If it was not the case, the shear would have been an obstruction for the bulk connection to induce a nicely behaved boundary connection. Let me tell you that it is also the case in ADS. In ADS, you can show that the boundary is embedded into space-time without extrinsic curvature, and then basically you have the Levi-Civita connection in the bulk, you have the Levi-Civita on the boundary, and everything is fine. But here you will see that the Levi-Civita will be a bit more complicated. So just to give you my notation, so this epsilon is the Carolian vector again, and it generates, so sorry for the pleonasm, but the null generator of Scry. I will define as well, because I will need it, a form which is dual to epsilon, which I refer to as a clock form, or better mathematically speaking, an Erashman connection, which will be acting on epsilon and give 1. So you see that if I'm just giving this definition, it's not unique, because I can always shift this clock form by something that is transverse to epsilon, and it will not change this definition. This is the geometrical origin of what is called the local Carroll boost. So you have seen in the lecture the global Carroll boost, which act on the basically on the flat manifold. You can realize this boost symmetry also locally on any Carolian spacetime, but then your boost parameter becomes dependent of the coordinate. And this is what is referred to as local Carroll boost. So now, since I have a notion of clock, which is okay, it's rather arbitrary because I am Carolian, but I define a clock, I can define, you know, the hypersurface of simultaneity for this clock. So it will be things that belong in the annulator of this clock form. So by which I mean it will be generated by vector that when acted upon with tau gives 0. And this, in the context of null infinity, is referred as cuts. So a cut basically at null infinity with sufficient smoothness of topology will just be a celestial sphere. By celestial sphere, I mean I'm sitting here in space-time, I fix my watch, and then I look up the sky in any direction. This is a celestial sphere at given time. Okay? So now I will basically choose a tetrad formalism because it will be easier, and I'm sorry if I go a bit too fast on the technical details, but it will be again reviewed next week by Professor Henneaux, how to deal with Wilbein basis in the context of Carroll. So here I will choose this adapted basis that I will refer to by E with an index capital A from 0 to 3, and the related dual basis as theta A. Then I will take my first vector to be aligned with the Carolian vector, my first one form to be aligned with the clock form, and then all the others are basically spanning the cuts. So then the metric will be only defined in the cut like this. So if you wish, these theta A are basically a Zweibein on the two sphere. And then since I have, you know, again, these Weil transformations everywhere, I have to assume that this vector fields actually transform also like weight 1 Weil objects. Okay? So this is just to settle my notations. So now I have a couple of symmetries to fix this basis. Basically, I have rotations, which is easy to understand because I can, always rotate my two space-like vector on the boundary. So I have my Carolian vector in that direction, and I can rotate my two space-like vector at any point. The local boost, I have already mentioned what it is, but it's just that I change my clock form by an object which is transverse to epsilon, because epsilon acting on theta A is 0, by definition. So basically, if a choice of clock, which is related to the Carolian arbitrariness of time, is in one-to-one correspondence with the choice of distributions of cut at null infinity. And then I have, again, these Weyl transformations. And to end with, I have also boundary diffeomorphism that are induced by the change of coordinate freedom in the bulk. And then I will play with all these symmetries to constrain my variational problem, basically. Okay? So maybe let me skip this for the moment because I will not need it. If I have time, I can always come back. So now we have discussed about the kinematics, right? It's important now to discuss about the way the gravitational field will manifest itself at the boundary. And as in the bulk, it manifests through the connection. So just to fix in the notations, I will define my connection one form as follows. So the action on EB with the connection aligned to EA will be omega CAB aligned to EC. And I will take these functions and I will store them in this kind of one form, which is sometimes referred to as the spin connection if you are dealing with fermions. To preserve Weyl invariance, I will also need a Weyl connection on the boundary. So I will basically take the pullback to infinity, I denoted by iota star, of this capital A, which will give me something that I call alpha. And it transforms in the same way. So then I will be able, for any connection that I built, and I will give you some hints how to build it, I will be able to improve it in this curly D operator by adding a contribution depending on alpha times the weight of the fields. By which I mean, if I have a field phi that transforms under Weyl transformation as a Weyl weight W field, sorry, so by which I mean exactly this, so B to the W times phi, then I'm sure that this operator will preserve this transformation, which is not the case of nabla, because the bare nabla can still act on the B. So for example, I will denote, the Weyl covariant derivative of the metric as follows. And since the metric transforms with a -2, I will have a -2 here. And now the vector transforms with a +1, so I will have a +1 here. So now I have a legitimate question for you. So I am on my conformal Carolian null manifold, and if I provide, the way the metric and the null vector are parallelly transported by this curly D operator, and also the torsion, because usually I need the torsion as well, then am I able to completely determine this curly D operator? In Riemannian geometry, the answer is yes, actually. I will review why. But in Carolian geometry, no. Because basically, there is no inverse metric. So why it is the case in Riemannian geometry? So the thing is that if I denote by this T ABC the torsion and this X ABC, so the parallel transport of the metric, which is sometimes referred as non-metricity, then what I can show by computing some combinations of this X, which is precisely this one, actually, this one, I can derive this equation. It's a really simple computation that everybody has done in a differential geometry lecture. So then, if I have an inverse metric, I can basically raise the C index, and then I get omega CAB in terms of the metric, the torsion, and the way the connection plays with the metric. The problem is that in the Carolian case, I cannot raise this index. So I cannot basically have this statement, which has been referred to as the fundamental theorem of Riemannian geometry. So now the fundamental theorem of Carolian geometry, if you want, will tell you that actually this equation, will imply some constraints among the fields and the geometry. And the constraint is as follows. So the only offending term here is when c is equal to 0. So by which I mean when you transvect this omega CAB with the epsilon vector, which is the null vector. And then if you do that and you massage a bit this equation, you will find this, where the sigma is the shear of epsilon, theta is the expansion of epsilon, and you have here contribution of the non-metricity. So basically, what this equation tells you is that you cannot achieve torsion freeness and metric compatibility if these terms are present. Okay, but so let's rephrase it like this. So a connection that will have no torsion and will preserve the Carroll geometric structure will exist at the only condition if the time component of the Weil connection is given in terms of the expansion of epsilon, and the shear of epsilon vanishes. Actually, and I've already told you, these conditions are satisfied if Einstein's equations are verified on the bulk. So by which I mean that actually I'm just presenting it to you as a general statement, but the general statement will not be an obstruction to me. But the problem is that if, you know, now I solve these conditions and I assume this, I will still have some freedom in the connection. So this is just for people that can read this kind of equation. For the other ones, just keep this as the take-home message. So basically in this part of the connection, so the omega A, where A again labels the spatial directions, I will have a part here which is undetermined by any of the aforementioned constraints. Why? Basically, here I have a constraint that is in 4 bulk dimension. I have two directions on the celestial sphere. So this equation is 3-dimensional because I have the symmetrization of 2 indices that goes from 1 to 2. So then if I have 3 constraints, that means that the aforementioned equation, this one, will be unable to constrain 3 components of the connection for me. And these 3 components of the connection are the following. So they will be actually the spatial symmetric part of this piece of the connection that is the only one that transforms inhomogeneously under boost, so we call it the boost connection. And from a geometric point of view, so what are these quantities actually? So now you can basically plug this boundary connection into the aforementioned Einstein's equation and solve basically the constraints you will get. And what you will show is that this CAB part actually is the only degrees of freedom that does not depend on the way you embed scry into the null boundary into the bulk manifold. For instance, this beta will depend on this embedding and is pure gauge. Actually, if you want to see that more clearly in coordinates, I refer you to very nice work by Marc Geller and Céline Zwickel here in the audience that prove that actually this degree of freedom was pure gauge. But the CAB is not. And the CAB is what? Is just the shear of a null vector which is pointing towards scry. Since it is part of a connection, obviously, you have still gauge degrees of freedom in this CAB because it transforms inhomogeneously under local symmetries. But what you can show is that there exists only one tensor in this CAB that is completely gauge and Weil invariant, and this is this News tensor. So again, it's kind of powerful because you know, only by studying appropriately the boundary connection and basically identifying all the degrees of freedom and the constrained fields in this connection with respect to the bulk gravitational field, we were able to extract, let me be a bit pretentious, but the ultimate definition of Bondi-News tensor, which is covariant under all the symmetries. So, okay, any question up to here for the moment? No? Ça va? So, let's go then. So now that I have introduced all this stuff for you, you will see it will be easy. So first of all, let me make maybe a summary of what I've been said in terms of 3 main lessons. So first of all, as I've told you, we have to work to do things properly in conformally compactified space-time. Because there you have the Weyl symmetry which is manifest, and you don't have to struggle with it as is the case when you work in a non-compactified and coordinate-dependent settings. And also the main reason is that the boundary does not even exist outside this conformal compactification. So second, you have, if you want to do things also mathematically properly, you have to work in a fully Weyl and Carroll covariant way like we did here. So that we are not relying on any gauge fixing, on coordinate choice, etc. So we are basically playing with the more general geometry you can scry with, but under the constraint that Einstein's equations are still satisfied in the bulk. And also, so this is a very important point, please do not insist on Lorentzian intuition. Because basically we are strongly evading any of the Lorentzian context you may know of in usual physics, basically because we have no conservation and we have a connection that contains degrees of freedom. Actually, it's not surprising because, you know, if you are dealing with Galilean physics, for instance, in Galilean physics, and in particular in Newtonian gravity do not obey the strong equivalence principle. So which means that the metric is not the only gravitational potential. And this is true because as you saw in this lecture also, is that you have degrees of freedom in the connection because of the non-invertibility of the cometric in that context. And these degrees of freedom contain the Newtonian potential. It's a bit the same here. You know, this CAB that I presented you in the Carrollian context is the analog of the Newtonian potential, but for Carrollian physics. So this is something that cannot be determined from the background at infinity. It's a piece of data on top of that, and there have been a lot of studies discussing these degrees of freedom in the connection already in 54, but it has just only been appreciated recently in the context of flat space orography, although they are instrumental in defining the correspondence. So now, let me come back to what I've reviewed in ADS. So I will assume that on my null manifold at infinity, I have a microscopic description of the boundary theory in terms of this field, phi. And the thing is that I will not assume anything about this phi except that they are local. Except of that, I don't have any control on the field content of my boundary theory. I will just assume that they are fields and they are local. And they are Carroll covariant, of course, because the whole action at the end has to be conformal Carrollian covariant. And then I will couple it to the geometry. So I'm working in the Wilbine formalism. So my geometry here will be the cotetrad, basically. So it will replace the metric in the notation I was using for ADS. And then since my connection has some degrees of freedom, I will work with a connection here, omega b, which is completely disentangled from theta. So actually, I have these two black terms like in ADS. So this is just the contribution of the field. This is the Wilbine equivalent of delta G mu nu T mu nu. And this is the additional term. So first of all, just to set down the notation, so I'm using the same notation as the famous Landau and Lifshitz series of books. So actually, in this T, so this T is again developed as a vector on the Wilbine. So the vector T0 has a purely temporal component, which is the energy, and a mixed component, which is the energy flux. The TA, where A goes again from 1 to 2 and describe the spherical direction, has a temporal component, which is the momentum, and a purely space-like component, which is the stress. So this is just the Wilbine decomposition of any stress tensor. Nothing new. The new stuff is coming now. So in this new term, basically, I have introduced variation of the connection, and then as a response to this variation, I have to introduce new fields. These new fields have been referred to as hypermomenta, and which are vector fields in in this fashion, you know. And again, let me stress that they are unavoidable since you have extrinsic data in your connection, which was not the case in ADS. So now I can basically ask, like I did before, that my boundary action obeys some local symmetries. And the thing is that I know a beautiful result, which is referred to as the existence of Noether identities, that for each gauge transformation, which I refer to here as Carroll boost, rotation, Weyl diffeomorphism, there is an identity satisfied by the energy momentum tensor, the hypermomenta, and also the equation of motion of the fields. So that when I put these fields on shell, I will get constraints, differential constraints in general, which will imply only the energy momentum tensor and the hypermomenta. So for instance, let us go back to this very nice example. So if I take, you know, this S, so this action, which is an action for the field phi coupled to the geometry G mu nu, whenever I vary with respect to phi, I get the equation of motion for phi, E phi. And then if I vary with respect to G mu nu, I get the energy momentum tensor. Okay, so it's exactly like that. You have to work at the boundary of ADS to reach the equation I've showed you. So now if you assume boundary diffeomorphism invariance, you basically say that delta psi of S equal to 0, and delta psi is what? It's just the Lie derivative. So bon sang. I think the batteries are gone, but I can show in that way if you will. Sorry. So you replace by the Lie derivative, you perform some integration by part, and you will get basically under this integral sign, you will get nabla T mu nu times psi nu, and you will get a contribution coming from the equation of motion. And this is the Noether identity I was referring to. Okay? So now if I put the fields on shell, this will vanish basically, and I will get the conservation of the stress tensor. Bizarre. So now I can do the same, but for all the local symmetries I have discussed. I'm just displaying the equation, I will not comment them. If you wish, we can discuss next week about that, because I think it's better that Professor Henneaux basically derive this equation without the right-hand sides, and then we can discuss about this right-hand side. I'm just displaying this equation because they are needed to prove the master equation I want to discuss. So just for the sake of completeness. So now the most interesting one to my taste is the diffeomorphism, is the one that you get from diffeomorphism invariance. And here you will have two terms. So you will not have only the conservation of the stress tensor, but you will have an additional term in red here coming from the variation of the connection under diffeomorphism. And so if you work out this term, basically, using Carter magic formula, so it's a 5-line computation, basically, you will get this beautiful equation. And something that has been already appreciated by Duval and Kunsel in 1974, actually, so it's a long time ago, when they were dealing with Galilean fluid dynamics, is that if omega AB, so the connection, is not completely determined by the background geometry or the other fields in the variational principle, the right-hand side in red cannot be recast as a divergence. So by which I mean that this term cannot be written like the curly D dot of something. Because if it was the case, I could bring it back to the left-hand side, and assume that I have a conservation equation. So, you know, this is the mathematical origin of this flux-balance law story. You have a flux at null infinity because your connection is not fully determined by the background geometry. So then now, just to talk a bit about holography. So our main result was, so first to derive this equation, actually, in a Carolian invariant setting, and then if you provide the right holographic dictionary between what you can measure in the bulk, which is called the gravitational momenta, so the gravitational mass, angular momentum aspect, etc., and the Carolian momenta and hypermomenta, you know, the tribe of peace I've displayed you in the previous slides, then the boxed equation are exactly the BMS flux balance law I have displayed you at the beginning of the talk. These are the same, without any hypothesis on top of what I said. And the holographic dictionary works actually in the same way than in ADS-CFT. The thing is that you have to trade the boundary of ADS-CFT for a shear-free conformal Carolian manifold. That's life. Then you feed your Carolian momenta by some stuff that you pick in the third subleading order of the metric, like in ADS, and you have to take care of these hypermomenta, which are only turned on by the presence of these degrees of freedom in the connection. So we did this work for you, and then so we did it basically in its full glory, in its full generality, but we presented it in a boundary gauge fixing that amounts to say that the clock form is exact actually, so that we have a coordinate on the flow of the Carolian vector epsilon, and that we choose that epsilon is without expansion and beta is 0. So it's just a choice of gauge, if you wish, which is referred to as a Bondi frame in the literature. But if you do that, what you find is that the Carolian momenta are given in terms of the BMS momenta computed 15 years ago by Glenn Barnish and Cédric Troussard. These are these green pieces. And then all the yellow, you know, these yellow pieces are basically given by the constraint I have displayed you here. So the constraint on the first box in this slide. So this is just a technicality, but which means that we don't have to add a lot of things by hand. Everything falls from the formalism. Then now what is the question of hypermomenta? So the hypermomenta are even more interesting because the hypermomenta are defined as follows. So the purely space-like part is just the curl of the shear, actually. And the 0A part, let's say, so the part which is related to the boost connection, is nothing but the Covarnian-News tensor, plus a term that is forced to be there because of the constraint imposed by the symmetries. And the thing is that this object, actually, if you take the derivatives, because you see that here they will, so I will show then again, they will always appear like derivative in this constraint equation. Actually, when you take the derivative of this object, you find what is called the Coton tensor of a Carolian geometry. So I'm just telling that for aficionados and for people who are really interested in this, but we have actually proven something that was discussed by Marios and friends since a couple of years now, that the radiation of the boundary can be tested as a non-conformal flatness condition. Why? Because, you know, in 3 dimensions, so my boundary again is 3-dimensional, the Coton tensor gives a measure of the possibility I have to take a representative of the boundary metric, do a conformal rescaling, and get back to the flat metric. Whenever you have radiation, the metric on the cut cannot be conformally flat. This is it's not only a statement about the metric, it's a statement about the metric, the connection, and the null vector, of course, because it's Carolian. Okay, so we are really happy about that because now we have an understanding of the fundamental origin of this equation in a fully Carolian covariant setting, and you have even a purely boundary geometrically motivated condition for non-radiation in flat space-time. So let me basically wrap up in giving you the main punchline here. So I will not repeat the first one because I have already said it. The second one I will repeat it because I think it's important to flash this point. You have to introduce this hypermomenta if you are dealing with non-Lorentzian physics. Full stop. Because this hypermomenta, for instance, in the context of Galilean field theory, for instance, will encode a lot of very well-known phenomena like Coriolis dragging or something like that. And if you have Newtonian gravity, they will also team up with the Newtonian gravitational potential. So I think whenever you are dealing with a connection that is not completely determined by a metric or a background structure, whatever it is, You need to introduce this hypermomenta to be sure that you are not overlooking some degrees of freedom. So the third point, it's again a spoiler with respect to next week's lecture, actually. So what will be shown in next week is that if you don't introduce hypermomenta, and you just consider the energy momentum tensor by itself, the Noether identity for local Carroll boost invariance implies that this pi A, which is the energy flux, is vanishing. Of course, at null infinity, we have seen that it cannot be vanishing, actually, whenever this new tensor, which encodes gravitational radiation, is present. But we were able to prove that this equation, actually, is not in contradiction with boost invariance. Actually, it's implied by boost invariance, but at the price to introduce an hypermomentum. And then also, the fourth point is maybe some teasing regarding work in progress. It's that since the hypermomentum is related to variation with respect to the connection, and the way the connection couples with the field depends on the typology of the fields, basically, thanks to the expression of this hypermomentum, we can have access to, or maybe have some hints, let's say to be fair, on the microscopic theory that you have to put on your boundary. And this is really important, for instance, to encode radiative amplitudes on the boundary, like gravitons or photons, etc., which are referred to Carolian amplitudes and which are really, really well studied nowadays in this flat space holographic correspondence. So maybe just before finishing, if I may, this work basically allows me to dream of a full picture of the boundary theory. So we have discussed about this radiative sector. This radiative sector is part of the extrinsic degrees of freedom that you put on your boundary, are part of the connection. And in this paper with Laura Donnet, Yannick Herfray, and Romain Rozziconi in 22, basically, we were able to prove that this field actually belongs to time-like or electric, in the wording of the lecture of today, electric Carolian field theories. At the mechanical level, these electric theories describe something like phi ... equals to 0. So this is something that is immobile like a particle or like a field. It will not move in space, basically. So you can see this object as basically defined on null infinity like data, Cauchy data on early and late constant time hypersurface, but pushed toward their null limit, basically. So this is exactly what is done in the scattering amplitude story. So you prepare your state at null infinity, and then you let things scatter, and you encode these scattering amplitudes as correlator at null infinity. So all this is coherent, you know. And so if you want a theory for that, it will be a dynamical theory for a connection. Let's say a twisted avatar of Chern-Simons, because Chern-Simons is not dynamical. But so it will be something like that. And we are working on that right now. A paper should be published in summer, I hope. Then you have the Coulombic sector. The Coulombic sector is basically what has to do with mass, angular momentum, etc. And mass and angular momentum are thought to be, you know, more related to the other type of representation of the Carroll group, or the other type of field theories, which are the magnetic ones, or the space-like ones, if you wish. In this case, Marios and collaborators in this very old paper, not very old, but a quite old paper with respect to the lifetime of flat space holography, have been proposing to consider this representation not as particles that move like instantonic tachyons, but rather like extended objects, like brains, for instance, space-filling brains. So they are still instantonic, but they are not particles. They are completely delocalized in space. What we were able to show in this paper by myself, Mathieu Villat, so one of the co-authors of this paper, Marios, and our student in Polytechnique, Victor Chabiran. So we were able to prove actually that if you consider a theory for these brains and you basically study the way they interact, and you redo basically Boltzmann analysis, but with brains instead of particles, we were able to prove that the evolution equation along Scry in the absence of gravitational radiation in the bulk, was exactly encoded as the dynamics of these brains. So this is one talk per se to discuss about this paper. It's just to flash your attention, to drag your attention on this particular thing. So now we have two types of representation, two types of understanding of what kind of field to put at null infinity, what kind of representation of the Carroll group to put at null infinity. The best thing we have to do is to see how to couple them and to recover from our microscopic analysis these flux balance laws equation. So this is part, roughly speaking, of work in progress with, again, this team of gentlemen, including the student. And so, apart from that, which is my personal perspective, I can give you other perspective. For instance, how all this story of hypermomenta, etc., team up with the asymptotically flat limit of a DSCFT that a lot of people did, but in the way I was presenting it, we initiated with Romain and Geoffrey in this paper of 21. I'm just quoting the paper with Romain because it was done in a more... it was really presented as a program in this paper, but it was building on an earlier paper, and also a lot of work by Marios and collaborators. Then we have some Dutch friends, Hartong et al. 25 there, that have been studying also some kind of holographic renormalization adapted to this null geometry, and we're trying to understand if this stress tensor that we defined is or can be understood as an avatar of the Brownian stress tensor that appears on null hypersurfaces. To me, it's still not clear, so it's part of the reflection I would like to push. Then the third point, it was the previous slide. And then also something that will be really appealing for people in the audience, like Céline, for instance, will be to apply this to finite distance null hypersurface, for instance, black holes that are in equilibrium with infalling matter. So then whenever you have infalling matter, you will have, or infalling light rays, if you wish, you will have again some non-equilibrium things happening at the horizon. So you will need hypermomenta and variation of the connection to take care of these non-equilibrium things. So I have the impression that this paper was only the beginning of a very nice story. I don't know if you share this impression, but actually I will personally continue into that direction because I strongly believe that this is the direction that is to be pursued, to not to conclude that flat space holography works or not, but to give enough technical material for smarter people to reach this conclusion, or a bad one, I don't know. We'll see. And on this perspective, I would like to thank you for your attention, and I will conclude here. Thank you.